You do what you want. Yeah. All right. So I think we're getting 2 minutes away. So let's.
Thank you very much, Philip. And so, welcome everybody. I'm Francesco Zappa. I work at Facebook Research in Paris, and I've been, and before that, I've been researcher at Tyrvia for a long time. And in this talk, I will tell you some stories about the dwarf debugging format for stack unwinding and some allocation. And I hope it will be fun. And first of all, this is some work that has been done either by Greg Clayton at Facebook or by me with my colleague, with two fantastic colleagues, Phil and Stefan, when I was back at Tyrvia. So let's start. I'd like to start from something that we all understand. We run a program and we get a segmentation fault. This is something that happens very often. And we have, since we are computer scientists, we usually ask, give me a backtrace, and we get a lovely backtrace, as this one. And again, since we are computer scientists, we know how to interpret these magic numbers, okay? These magic numbers are actually information which is stored in a structure, which is the call stack, which is stored in main memory. And these actually are the return addresses that have been stored in the stack frames. Okay, so far nothing new. Now, the question that I want to ask is, now I'll give you a call stack like this one, because your application crashed. Is there a reliable and efficient way to produce a backtrace? So you will say, if you have a frame pointer, that is a pointer that's registered that points here, then yes, you just read that and follow the chain, and it is super easy. But my question is really, what if you don't have the frame pointer? Is there a reliable and efficient way to produce a backtrace? And then it is not so easy, because all what we have is a stack pointer here, and we have no clue about the size of each call stack. But we are lucky, because there is one gadget which is called dwarf unwinding tables that can help us. How does it work? So first of all, let me say that you can take any binary and ask for this table with readf minus wf or objdump or whatever you want. And what's the trick? What are these tables? This is the kind of information that you get. Basically, you get a table in which, for each instruction, which is identified by the program counter, you get what? An expression that specifies how to compute the location on the stack of the return address. In this case, for this instruction, we know that we should take this, the RSP register, we add the constant 56, and we subtract 8. That will give us the address where the return address of the current call stack has been stored. This is great. This solves our problem, okay? And looks easy. The first thing I want to say is that this is relied upon to implement stack unwinding, of course, by debuggers, but also by pretty much every program analysis tools out there. And much more interestingly, it is relied upon by the C++ runtime to implement exceptions. So let me say it again. It is relied upon by the C++ runtime to implement exceptions. What does it mean? This means the first takeaway of this talk, straight away, is that debug tables are not only for debugging. Debug tables can be used for debugging, for analysis, and by the runtime of your programming language. Okay, so now debug tables are getting much more important. How do they look like? Then, so I take Linux, so it will be an ELF binary. So this is my binary. I have a lot of different sections. Okay, we all know them. In the text, there is a code. In the syntax, there is a symbol table, dynamic data for dynamic linking, and so on. And there is one section, which is hreframe, that contains the table that I just showed you. Really? Well, let's look at it. Let's do an object dump. If we do an object dump, we don't get the nice table. We get this binary blob, okay? Not a big deal. We pick up the standard, we write a parser for the dwarf format, and what do we get? We get this. After parsing of the table, we don't get the table, we get this. What is this? CFA offset, CFA advanced log, CFA def, CFA offset, CFA expressions. So what is this? This is bytecode that is interpreted on demand by a special state machine to build the table on demand. What's the point? This is much more compact than the table. The table would be huge because for every AP you have to store all the information about the return address and all the register. While here, this is a much more compact way. And what can we observe? So it is bytecode, and it contains arbitrary expression accessing register memory location. So it is a stack machine. So what you get? This says that to compute the offset at this address, what do you have to do? You have to push the stack pointer, you have to push the instruction pointer, you have to push the constant 15, you have to do an AND, you have to push the constant 11, you must do a greater equal, and if the result is true, you have to push the literal 3, do a shift left and do a plus. Wow, now this is a bit insane. So, second point I want to make is that the table is not stored in the table format. It is stored as bytecode that is interpreted on demand to inspect the call stack. And this actually stack-based machine is, for fun, Turing complete and can dereference memory and access values in machine register. And this machine lives in a place that you would not expect. I mean, it lives in the heart of your binary. What's going on? Let's try to dig more. So the first thing, if you want to know more, the first thing you realize that it is badly specified because there are two subtly incompatible formats. There is a debug frame, which is what has been formalized by the standard, and there is hreframe, which historically is whatever GCC implemented. And the two formats are almost the same, but not quite. And hreframe, which is the de facto standard, is basically, to the best of my knowledge, only described in this blog post. Jan Lance Taylor, when GCC generates code that handles exceptions, it produces tables that describe how to unwind the stack. Yes, these tables are found in the hreframe section. Hreframe section is very similar to debug frame, but not precisely identical. And I don't know of any documentation. So in the blog post, he explains a bit more. But yeah, it's getting a bit fishy. Let's dig more. Point number 2 is that it is a burden for the compiler to generate. Why? Because basically the compiler now is generating code for your processor, for x86 installed, and for the dwarf unwinding machine. And each optimization pass must keep the two in sync. Okay, now this is getting weird. And if we, for instance, ask GCC to compile one file, and we look at the assembly, then we have in black the assembly that we all know that is taught at the university, but we also get interleaved this weird instruction that I put in red that begins with CFI. And what is this? These are the bytecode instruction for the unwinding machine, for the stack unwinding machine. Okay, so basically your compiler is not just one compiler, it's two compilers. It is a compiler for x86 and a compiler for the stack unwinding machine. And each compiler pass must update both of them. And if you're into security, then this is a potential vector for arbitrary code execution. And there was a proof of concept attack that was built 9 years ago. It is not so easy because you can read, you cannot write, but you can make the unwind exception handling mechanism jump where you want. I mean, read the location that you want. So it is actually possible. And Usenix Oakley Bratus, this paper describes how to do. And the baseline is that all this is complex, buggy, and untested. How complex, buggy, and untested? Well, a few years ago, we could ask Linus Torvalds, why doesn't the Linux kernel rely on dwarf tables? And on the mailing list, he answered this: sorry. So Linux kernel, Linus Torvalds, kernel mailing list 2012. Sorry, but last time it was too painful. The whole and only point of unwinders is to make debugging easy when a bug occurs, but the dwarf unwinder at bugs itself, or our dwarf information at bugs, in either case, it actually turns several trivial bugs into a total undebuggable hell. Okay, this is the state of the art 2012. Basically, it says it is not reliable. And what I like is that this email goes on, and it completes with, if you can mathematically prove that the unwinder is correct, even in presence of bogus and actively incorrect unwinding information, and never ever follow up at pointer, I will reconsider. So what we tried is to make Linus Torvalds reconsider. Basically, can we make dwarf unwinding reliable? Project number 1. The compiler generates the table. Can we validate them? Can we check that the tables are correct? So to understand how we can do this, we have to, let's take one binary. Here we can see the assembly. And let's suppose that the h-frame table has been generated by the compiler, and that we can interpret the h-frame bytecode to generate the unwinding table. So we have the parser is correct, and the compiler generated it. And this is a table that has been generated. Let's try to understand how this works. So what we know is that upon entering the function foo, we know, these are the calling convention, that when foo is called, before executing its first instruction, the return address is stored at RSP. And indeed, what do we have? We have that the expression says take the RSP, add 8, subtract 8, so RSP, exactly. Now let's imagine that we execute the push instruction, push of register 15. What happens? Well, the stack pointer moves. It is decreased by 8. And indeed, if we move to the next instruction, RSP has been decreased by 8, and the expression tells us RSP plus 16 minus 8, which is what we would expect. The return address is stored at RSP plus 8. Let's go on. Push, again, moves the stack pointer, so we get another expression at RSP plus 24. What else do we have? Now, move doesn't touch the stack pointer. So after the move, the table still says RSP plus 24 minus 8. Okay? So I believe we have understood how this works. And we can make one remark. The unwinding table itself is completely redundant with respect to the binary code, because it just captures some abstract execution of the code. That's the key for validating the table. All the information about where the return address has been stored is already in the binary, in the assembly, okay? So, question. Let's do something else. Let's do a different exercise. Let's take this instruction, random one. And let's suppose that we know that in an execution, the return address is stored at some memory location, 1158. And what we can do, we can access the stack pointer and maybe store FF1000. We can do the math. We can do 1000 plus 160 minus 8 and check if we get 1158. Okay? Why? Because evaluating if the table is correct, when we evaluate the entry on the current register values, then this should compute the concrete address of the return address, where the return address has been stored. Okay? And this gives us a key to implement a tool that can validate dynamically the unwinding tables. How? Well, we have to define our abstract execution of the code. How can we do it? Well, the abstract state is a stack. We take just a stack of concrete addresses where the return addresses have been stored. Okay? It is just, imagine, your call stack reduced to the addresses where the return address is stored. And the abstract instruction semantics is, well, for call, it pushes the content of RSP on top of the abstract state. What call does. And read, I mean, it is not what it does, but it is an effect in this abstract machine. And read just pops one value from the abstract state. And if we have this abstract state, at every instruction, we can validate the table. How? We just evaluate the return address H-frame entry for IP, and then we compare it with the value in the abstract state. So now there is some care for the collisive register, but that can be done as well. And what we have done is first thing that we have implemented a tool whose goal is to validate H-frame entries along one execution path. Okay, how is it done? Well, it was proof of concept. So we took GDB. It can do step-by-step binary execution and gives us access to the processor state for free. And then GDB can be scripted in Python. So we wrote a Python driver that parses self and dwarf. It evaluates the dwarf expression and scripted GDB to implement the dynamic analysis I sketched in the previous slide. The result. So before you ask, it is super slow. It can process a few thousand of assembly instructions per second. So, but this is good for now. This is good to do fast testing of your compiler. And as an example, by taking the excellent sysmys and creduce and our tool, we were able to generate this program, several nested loops, some mass. This is the kind of thing that gets on which the optimizer might get confused. And what happens? If we compile it with C-Lang 3.8, which these days is a bit old, but still, what do we get? We get this assembly and this unwinding table. Let's look at it. Let's suppose that the abstract state is FF1000. We execute this one. RSP is, we read it from GDB, tells us what RSP is. We check it, we do the math, 100 plus 8 minus 8. Yes, it coincides with the abstract state. All good. Let's move to the next instruction. GDB again tells us, okay, RSP now is 0FF8. So we do again the math, plus 16 minus 8, and we discover, yes, good, let's go on. I skip a few hundred instructions, and then we get here, and we have FF8, 100 plus 16 minus 8. Everything is fine, but this is what I want to point out, pop. So pop increments RSP. So this is good. But when we move to this instruction, we have the abstract state is unchanged. RSP is now 1000. And if we do 1000 plus 16 minus 8, bam, this is incorrect. And the tool can reliably flag that here in this instruction, the debug the dwarf unwinding entry for instruction 40061E is incorrect. Okay, because this pass. Okay, this was able, using this, we were able to report a few bugs on Silan. It was fun. This happened at 00, 02, and OS, but not at 01. And we said, no, this is interesting, but it was just a coincidence. It was the fact that that -01 RBX was not saved, so this instruction didn't exist. Now, this bug is cool, it has been fixed. And the point is that it is possible, since the table is completely redundant with respect to the binary. Given a binary, given a table, we can match the two and validate the table. Now, it is not also good. Why? Because generating the table itself is a burden for the compiler. And some compilers do not generate H-frame at all. OCaml H-frame code, for instance, was contributed by Jane Street. And why? Because they wanted binary profilers. And something else, a JIT will not generate the dwarf unwinding table. So did you ever attempt debugging JIT-generated assembly that was incorrect? Oh, super hard. You get a blob of memory and you don't even have a stack trace. And you have to do lots of kung fu in this case. Or something else, if you write inline assembly, now it is your role to manually code also not only the assembly for x86, but also the unwinding instructions. And let's look at an example. So this is a bit of glibc in define the low-level log.h. So what is this? Let me say, this has been written by someone who knows what he's doing. Basically, this is the encoding of this bytecode program, of this dwarf unwinding bytecode program. It has, as I said, been if you try to decipher it, is super clever. When it tries to, since there are lots of different macros, it tries to be generic. It is super clever. It has been done by someone who knows what he's doing, but despite this great care, there is an off-by-one offset error, which result in, if we breakpoint at some point, okay, like some instruction, and we ask the backtrace, we get a duplicated entry in the backtrace. Now, GDB is super robust. So basically here it is dereferencing not the right memory. It realizes that there must be something wrong and tries to fix it steps. But any other program analysis tool would probably follow a byte pointer here. So this is a problem. But let's think, if the table is redundant with respect to the binary, maybe we don't have to need the compiler to generate it. We can just take the binary and generate the table ourselves. Can we do it? Yes. And the synthesis strategy is certainly simple. Why? Because upon entering a function, we know that the return address is stored at RSP, which is traditionally encoded with this RSP-8 plus 8 trick. And then we can do the synthesis by checking the instruction. Basically, we do symbolic execution. We check the execution of each instruction in each basic block. We check, are we using the base point, RBP as base pointer? In that case, do something. If we are not using RBP, then do we modify RSP? And in the two cases, we update the computation of the CFA accordingly by using the symbolic semantics of our assembly. And then we chain across the basic blocks following the control flow graph. Simple example, here we enter the function. We know that RSP plus 8 minus 8 because it's free at RSP. We synthesize the basic block, it changes to plus 24, and then we propagate it across the flow. So we get plus 24 minus 8, propagate on the arrows. We can synthesize here, and here we get minus 8, minus 8. We propagate this again. Here we end up propagating plus 24 minus 8. And look, they match. If they would not match, there would be a problem. Okay. So at the join point, you should always get the same expression. And let's look here. It is a loop. We get to plus 24 plus 32 plus 24. And at the end, we end up propagating plus 24 minus 8. And plus 24 minus 8, again, at the join point, we get the same expression. If at the join point, we don't get the same expression, there should be something super fishy in the sum. And we can terminate the synthesis of the program. And I love this. The fixed point is immediate, no need to iterate. And how can it be immediate? Well, because in some cases, the compiler cannot know the size of the stack frame. And like if here we allocate on the stack something which has some variable size, some unknown size, then in that case, the compiler must still be able to access this data. And it will stop using RSP as pointer to index the core stack, all the data in the core stack. It will just backtrack to RBP, even if you specify omit frame pointer. Okay? So this is a reasonably easy case. We have implemented this on top of CMU's binary analysis platform. It is a proof of concept implementation. In theory, we should do symbolic evaluation of assembly, tracking register, and so on. In practice, we were able to pull it off by implementing a heuristic that is aware of a few assembly patterns. And let me do a quick demo. Okay, I hope you can see here. Here I have a program which is demo.c. There is a function main that calls foo, that calls bar, okay, that does something. Let's compile it in the evil mode. So no asynchronous, no debug table, and no frame pointer, okay? It compiles. Let's run GDB on it. GDB demo, let's breakpoint on bar. Let's run. Okay, let's ask about trace. So it is almost correct, but not quite. Bar foo, this is definitely a bad pointer. So this is GDB trying to guess at its best, okay, with some heuristics. And if we move a little bit in the binary and we ask for a bad trace, then GDB, I mean, doing things gets super hard, and there are lots of bad pointers that will be followed. Okay, so this is good. Yes, and what I will do now, I will please synthesize information on this program. Synthesize the table on this program. So I get another binary, which is demo.eh. We can ask for the table that we, and now there is a table that has been synthesized by our tool, and if we invoke GDB on demo with the synthesized table, we do the same thing: breakpoint, bar, run, backtrace, bar foo main, lovely backtrace. Let's make it harder. Still correct. So synthesis work, and it will also work on more complicated programs. Okay. Try it out. It is available on the project webpage. So, what can we do? We can validate the unwinding table against the binary code, and we can synthesize the unwinding tables from the binary code. This allows us to identify bugs in the generation of tables, makes unwinding tables available to systems that do not support them, might integrate with compiler inline assembly extension, for instance. These are cool projects we might do, so that the poor programmer doesn't have to write the bytecode instruction, the dwarf bytecode instruction whenever he does inline assembly. Or we might be able, when we have to debug JIT code, we synthesize the table on the fly, so that only when debugging. Hey, so these are cool application for this. We can do more. Dwarf bytecode. bytecode. I mean, it has to be, when we want to unwind, we have to interpret all the dwarf bytecode, and this is so slow. If we use a standard implementation, which is libunwind, it does super aggressive caching, but then it is still too slow that, for instance, the perf profiler, when it tries to reconstruct the code graph, it cannot unwind the stack in an interrupt handler. And what does it do? Well, it copies the stack up to some desk offline, and then it does all the processing later. Now, if you are into security, this is very bad because you're copying potentially private data somewhere else for offline unwinding. And again, it is definitely suboptimal. We're copying to analyze. I mean, why can't we analyze, build a course about trace on the fly? Okay, and yes, we can. There are things that we can do. And which is the idea? Well, the bytecode is just bytecode. Can't we, that we have to interpret? Let's precompile it. So usually this is bytecode. It is interpreted to generate this table. What we can do, and it is interpreted when we have to unwind. What we can do is that ahead of time, we can take the bytecode, generate C code. I won't comment it, but this, there is a one-to-one correspondence between this and this. And what we do, we take the age frame table, we compile it to assembly, actually to C, and then we compile the C to assembly. We store this in a separate SO file that we called EHELFs. And we also wrote a libunwind extension that can read our binary code, okay? And now unwinding is just jump to this assembly to give you, with the proper context, it will give you the address that you're looking for. And we try to do things nicely, so it has the same API as libunwind. It is almost a relink and play replacement. Does it work? Well, it's tricky because you get a huge amount of code if you do this naively. And so we do a few tricks. We do code outlining at compile time. For instance, on libc, out of 20,000 entries, there are only 300 which are unique. And this is something that allows us to shrink a lot our SO files. And then we also implemented the explicit binary search rather than switch, because to keep the search compact. And which is the result? We get a 13 times speed up on libunwind calls made by perf gsym. If we, so gsym might be a standard application, not many function we encode just. And perf, I mean, the perf ends up spending 30 times less time doing the libunwind. And on some more evil case, like perfect bench, which is really good, the stress is the call, the stack, then we get 25 times speed up. Okay, here because caching is less effective. And it's a price to pay, 2.5 times space overhead. So, pro and cons. Okay. But what I want to tell is that there is a lot to do in the area. Okay, and if these projects, validation, synthesis, speeding up, I mean, are kind of academic prototypes, I'd like to complete this talk by pointing out some other work which is actually in use. Now there is another, I will move away from unwinding. I will go to another table in the DWARF standard, which is debug line, which is used to synchronize source and object code. How does it look like? Well, we had our binary, and this says that address 8048604 points to file and .c, line 5, okay? Line 10, line 9. This is what this table gives us. It is vital. You have an IP address, you want to know which file, which function, which position. Okay, it is another super widely used table. Okay, and how does it work in the dwarf standard? Well, let's try. This is our dwarf. Let's take one IP address. Let's try to symbolicate it to understand which file, which line number. So the first thing we have to do is that we have to interpret debugger bref, because every time you want to parse dwarf, you have to read all this. So you end up eating some memory. And then you have to scan all the debug info section to identify the correct compile unit and find the offset in this other table. So we get more accesses. And finally, we can interpret the corresponding debug line bytecode. Okay? And we get our answer. We get un.c line. Okay? But basically, we have touched a gazillion page tables to be able to do this mapping. Can we do better? The answer is yes. And it is a format which is called gsym, developed by Greg, and which has been open sourced in LLVM. What is gsym? It is an efficient file format for, let's forget dwarf. Let's reinvent a proper file format for retrieving data for addresses. And right now it implements source file and line. Will be updated soon with unwinding line call stack. In itself, it is not a replacement for dwarf. It is specialized for these tasks. How does it work? So we have seen, this is the standard dwarf. We have to touch pretty much, we have to touch a lot of different pages. The same information encoded in gsym. Well, we have to read a little bit in the header and a little bit here, and we get the answer. So the whole format has been designed to touch as few pages as possible when doing lookups. It is super clever engineering. Size, this is actually in proportion. This is realistic. It is basically 7 times smaller than dwarf and 3 times smaller than breakpad. And how is this possible? Well, lots of cleverness in the design. So the address table is stored as a sorted array of address offsets, which gives us efficient search, and also fast and easy linking, because since everything is an offset, you just update the base one when you do the linking, and you can recompute correct all your addresses. And then we get, it relies on space efficient encodings. So all strings are unique, file names are split in directory-based names, so that it compresses much more nicely. And even the encoding of the offset is compact. There is unneeded data, which is part of dwarf, which is not stored in gsym. And what is also nice is that it can be extended. The format is open. There is one data structure. You can add your own entry to the data structure. And for instance, it might be used as accelerator for accessing existing dwarf tables in dwarf files. And for instance, can point to, can include dwarf information in itself. It is what we want to do. And what I want to say is that it is open source for easy inclusion in Clang, LLD, and other LLVM tools. And it is easy to include in your workflow, because this is an example. If you want to do a lookup, then you ask a gsym reader, gsym, some file, gets memory mapped, can be shared between threads all nicely. And you just ask lookup for this address, and you get the lookup data structure that you can then do what you want with. And even creating file, there is a very simple API, or you can use dwarf to gsym to convert dwarf to gsym whenever you want, either at build time, or you might also do on demand and cache them. So you might use gsym today in your workflow and get to the benefit. I want to conclude. The takeaway. Dwarf tables are written at the heart of our computing infrastructure. This might be surprising, but it is true. And they are poorly specified and badly designed, at least for today's purposes. They are pervaded by subtle bugs. They're mostly ignored by the research community, and they are not understood by most programmers. And there is a lot of space for improvement, which means exciting research and lots of potential that can be exploited. Thank you very much, and time for questions.
Thank you, Francesco. I saw that Ed, right, wanted to ask a question. Is he still there? Ah, his question was answered. Okay. Let me jump in and ask probably a question to get people going. Francesco, I was wondering, like, suppose you had a time machine and you could go back to the time when dwarf was invented. Okay, what would you have done differently? Like, suppose, and of course we don't have time machines, right? But in the end, the question is meant to start a discussion about how can, if we had control over it, could we actually get a different representation, maybe not use bytecode, but use something else that would be actually better suited to do the job?
Mm-hmm. Well, gsym is an example, basically. So let's go back in time. What was the purpose of dwarf? Well, basically it was designed, it's a format that has been designed to take as less space as possible on disk, okay? But still be extensible, because wanted to support multiple languages, multiple architectures, arbitrary calling convention, arbitrary language features, okay? And that where all the complexity comes from. For instance, the point of using the bytecode is that you don't store a whole line, you store just a diff with the previous line, okay? And this enables compression of, while being, I mean, by adding new bytecodes, I mean, new bytecodes are added from time to time to the standard, you can tweak and do something more magic, some special cases on some ad hoc embedded architecture that uses different format and so on. Today, in many cases, we have different needs, okay? We want something which is fast on one architecture, because we know that we are distributing a binary that runs on two architectures, and it is all what we want to support. Then we can drop all the extensibility part and design a format that it is just tailored to store that information. And we can be more clever about the search. I mean, our binaries these days are huge, okay? And we can be more clever about the search. We don't want to do a linear scan of all the addresses to find the entry in the line. We want to be able to just jump to the right information. This is what gsym does, and to some extent what our EHL thing does. So you don't have to do a linear scan of all the addresses. You do binary search to find the right entry. It's a huge improvement. You try to store the information in a more compact format. You can drop information. For instance, gsym currently doesn't support the column number. You just have the line number. You don't support the column. For many purposes, it is what you need. Columns are super hard to get tricky whenever you have optimization going on anyway. So line is probably the only information that you need. And I mean, you can drop some information which are part of dwarf, because you don't need for today's applications. And yeah, that's the idea. There is, I will post it later. There is a very nice entry in the LLVM, repo that describes how gsym is designed and why we solve the details. And it became obvious what are all the benefits.
Okay. I'm seeing there is a question here in the chat by Artem. Do you have a mass proof that you don't ever follow a broken pointer, and has Linus reconsidered?
A mass proof, I don't. I mean, if you do the symbolic analysis, the symbolic evaluation of your binary, then, and your symbolic evaluation is correct, okay, then that is a mathematical proof, okay, that your unwinding table is correct, because you're just mimicking the table. I mean, you are just abstracting the correct information. Now, DWARF allows you to store the same information in many different formats, okay? We will synthesize one correct way to store the information, which is basically just the entry in the table, okay? We won't use fancy expression as the one that I showed you. Why does the DWARF format use this complex expression? Again, because in some cases it allows some extra compression, but in practice it doesn't make a big difference. And so if the symbolic evaluation part is correct, then yes, it is, let me say, provably correct. If our tool doesn't do the symbolic evaluation, because we didn't want to teach you the assembly and all the x86 semantics, for GCC, we only had to add a few heuristics, a few ad hoc patterns, because the compiler don't try to be too clever about how to set up the call stack. Why? Because they have to find, I mean, they must be able to access easily where the local variables have been stored, where all the information lives inside the call stack. So the compiler doesn't try to be too clever. And by adding just a few patterns, which are all described in the paper, then we could pull it off. This morning I got an email saying, this is great, we want to run it over OpenSSH, and there is this pattern that is not covered. Okay, yes, okay, we can add it. It is pro and cons. I mean, for the synthesis, our implementation is a prototype. It is to show, look, this is possible. Can run it on complicated programs. I might run it on gsym, on substantial software. We didn't try to do the synthesis with our tool on Firefox. I'm not sure it would scale and how long it would take, but it is there. Thanks, Art.
I'm seeing here another question by Ed. One thing I wondered was what that RA column in the table was for. In the examples, it was fixed at 8. Under what circumstances does that value vary, and does that cause any issues for you?
Okay.
Actually, wondering the same, yeah.
Okay, let me share again the screen, if it is okay with you, so that I can show again the table. Let me just show this one, this video. Sorry. Let me take a real table. No, sorry, 1 second. I will share it properly. Let's share everything. Let's go. Okay, what idea here? This again, it is all about compression. What it is being done is that array stands for return address. So this is a column that explains, that gives the expression where the return address is stored. And this is defined in terms of another column. This C here stands for this column, CFA, that stands for canonical frame address. What's the idea? The CFA is basically a location which is invariant across all the execution of the program. Usually it is chosen as the stack pointer just before you do the call. Okay, what's the advantage of having pointing out this location? Is that the return address, if we have one location, if we can jump from the stack pointer to this invariant location, then all where the return address has been stored and where all the call saved register have been stored is invariant, doesn't change. I mean, so all this is about compression. The return address is always at -8 with respect to CFA, to this location. And what changes is that CFA is addressed at different offset from the stack pointer. Okay? And the advantage is that all the call saved register and the return address can be expressed in terms of the very same CFA. So that we don't, whenever the stack pointer changes, we don't have to explain, well, RBX is stored here, RBP is stored here, R12 is stored here, array is stored here, because, I mean, all this is invariant with respect to CFA. And the only column that we have to update is CFA. Of course, DWARF is super flexible. You might ignore CFA and express the correct expression in array. But this is what is commonly generated by compilers. It is basically about compression, about pulling out some information and then which is invariant. Hope this answers.
Thank you. Actually, let me come back to Artem's second part of the question. Has Linus reconsidered?
This I cannot speak for Linus.
But actually, I can probably I can follow up on this question and make it a little bit more technical. Which is related, it's related to this. I was wondering what, in your opinion, it would take to actually make it into the Linux kernel. I mean, that they actually use this technology in the Linux kernel, because kernel development might involve code that probably even messes with the stack. And so my question is actually more like, what kind of assumptions do you have in your tool, have you made in your tool on the structure of the binary that you're actually analyzing, right?
Okay, let me first answer about the Linux kernel.
Yeah.
While we were working on this, the Linux kernel, the Linux kernel has some analysis of binary sorry, one step backward. The Linux kernel want to support hot swapping of functions. Okay, and this means that the code, the size of the stack must be invariant to the meeting point or midpoint. What I want to say is that they were doing some analysis on the size that the binary, that the call stack, the shape of the call stack made sense compared to the assembly. Okay, they were basically doing the same analysis that we are doing. They are doing symbolic evaluation of the assembly. They are doing this using their own ad hoc thing. Okay, and they wanted to do this to support dynamic code update. Don't remember the name, but one kernel developer had an idea. We are doing this analysis. We are exactly synthesizing a dwarf table, a dwarf unwinding table. Okay, and what they did, they designed a new format which is called the orc, because of course orcs and dwarfs and elves and all this. So you get orcs, and what is orcs? Basically, orcs is a synthesized table that uses the very same technique that we used, using their own symbolic analysis. And basically, I don't know how relied upon it is, but it is some work that they did in parallel. And they do some heavyweight assumption about the control flow. I mean, they are part of this, is building the control flow graph. Because the symbolic part, the symbolic analysis, once you have your symbolic evaluation machinery, it is easy. What is hard is when you have assembly, is to compute your call graph, to know where you have to propagate. And so we use BAP and the magic that CMU's BAP does. And while they tailored the reconstruction of the call graph to the assembly which is generated by GCC when you compile the Linux kernel with the options which are being passed. Okay, so there is this distinction. But basically, people are moving towards this direction. So for your second question, what are we assuming? So our implementation assumes x86, assumes x86 calling convention, and trusts CMU's BAP to reconstruct the call graph. If BAP cannot reconstruct the call graph, then there is little we can do.
Mm-hmm, mm-hmm. I'm seeing here a follow-up by Julia on the assembly patterns. What would be a more systematic approach instead of those?
Yeah, symbolic evaluation. For the you just have a symbolic evaluation of the assembly. You know, what is annoying is that x86 is complicated. The assembly and writing a symbolic evaluator for that one is some serious work. But the org people did it for the instruction that they cared about. And I mean, but it means that you have to write your own decoder of x86 and do some work. And then the other part is, say, the control flow graph. I mean, when you have jumped to the content of array P of array X, you must have a super good static analysis to compute the superset of all the places, of all the values that array X that can be stored in array X, so that you can compute a superset of all the addresses of where you can jump. And compilers do it whenever you have a switch statement. I mean, depending. But in some cases, they just use a jump table, and then you have to be, your analysis that construct the call graph must be able to follow those pointers.
Sorry about the noise. So when I look at it from from a very sort of academic point of view, where I have this ideal world of I can change everything I want, to me this looks like what you are actually trying to do is it looks to me like there's a need for formalizing. There's a need for formalizing the ABI more thoroughly than it has been done before, right? In fact, what you're trying to do is you're trying to specify very precisely how the stack is being used in order to later reconstruct it, right, for debugging purposes and exceptions and whatnot, right? So this might actually also, your work might actually call for more work into that direction, right? In actually formalizing the problem properly in the right, and developing the right language for it, so that you can actually talk about it and then develop tools?
I believe there are two parts in this. One is the analysis part, properly speaking. And then there is the programming at large thing, is that all this has to play nicely with linking. All this has to work on real binaries. Okay, linking is something super complicated, and that has to be formalized as well.
Okay.
And there was a project by Peter Sewell with and colleagues in which they tried, Dominic Stephen, in which they tried to actually understand, formalize ELF and linking. Now, ELF is easy, it is a bunch of boxes, just boring, a lot of work, but boring. But linking is super complicated. A linker has its own scripting language. So you can, so linker doesn't take your binaries and combine them. The linker takes your binaries, takes a script, interprets the script, and according to those instructions, decides how to generate the outcome. If you want, I mean, that is part of the game. That's why it's super hard.
So the big game here that we are playing is to actually formalize the relationship between the source language and the machine language, right? With all the because that's what effectively is going on, right? Because on the machine level, you don't have any of these concepts that still exist in the source language. So it's all about formalizing that relationship.
No.
Mm.
Yeah. But then if you want to do an analysis at work, everything has to be compositional. You cannot just take the bunch of memory that gets mapped to memory and executed. That gets mapped to virtual memory and gets executed. Your analysis has to be compositional, has to work on all the O files, and you must be able to merge with information. Just to give you an example of how complicated just the dwarf thing is that link time optimization. At some point, compilers could implement link time optimization, and this is great, except that they could not keep the debug information in sync after the link time optimization, because it was it is the same problem to be done again on a different language. Mm-hmm. And official release of LTO was delayed just because of dwarf. Okay, and yeah.
I see. Yeah, I'm wondering if there's more questions here. Have you, Francesca, have you looked at other machine languages than x86?
The validation, since we have GDB as backend, we could run on, I mean, GDB was doing all the shielding of all their work, executing step by step, accessing the, dumping the register and so on. So we basically had just to teach our script to, if we wanted to support multiple architectures, we just had to teach our script, which are the calling convention, basically.
Exactly.
And we implemented it for x86 and Power because we had machines and it was easy to run stuff on that. The synthesis, so that shows that it can be done. If you can do the validation on a different architecture, you can do the synthesis. And we didn't do the synthesis on any other, or on any other architecture. The speeding up thing, well, again, you have to teach which are the columns that you want to store and so on. I mean, it is just work. It is not art, it is just work.
Mm-hmm. Mm-hmm. Do you think that the Turing completeness of dwarf is this actually necessary for doing what you're doing? Or could you actually, I guess what you are generating uses a very specific kind of
Yeah.
program, right?
Yeah, it is. Yeah. We generate the dumb-best table that you can basically, and it is what org generates and what gsym generates for line information. There is absolutely no need for all that.
Yeah.
gsym shows that by choosing a clever encoding, by using only offset, by showing, for instance, offset are stored, I mean, it computes which is the largest offset you need, and it uses a minimum number of bytes to store the largest offset. This kind of trick, it can get 7 times smaller than DWARF. So yeah, there is really no need.
Do the security issues go away that that were actually part of that paper that you cited, right? That you mentioned. Do they go away when you do that?
Yeah, of course, because you're not interpreting bytecode anymore. So what they do, what Bratus and Oakley do, is that they take basically they inject a bogus DWARF bytecode in a C++ program. And when there is an exception, basically they make the exception handler believe that the return address is stored somewhere else.
I see. Okay.
And it is. And actually, they show how you can implement a very tiny language by hijacking the exception handling mechanism. So as soon as you don't interpret, you're done. Okay. I mean, you don't have this security thing. What is for practical reason? It would be great if we could remove the copy phase from the perf profiler, because that has lots of security implication. Because you're copying memory to somewhere else. Maybe there was a password. It was supposed to be stored in memory only for very few seconds, only for a very super short time, and now it is stored until the end of the execution, and somewhere else for the offline analysis, and that is problematic for security.
Okay. Okay.
Pragmatically, that is a security that matters. Mm-hmm. The person who was working on perf at Google told me, yeah, we compile everything with a base pointer because that's an issue.
Okay. So I understood we have still 12 more minutes if we really want to use the whole slot. There's more time for questions, people.
I could jump in with a comment if that's all right.
Hi, Stephen.
Hi, Francesco. Nice talk. I suppose I wanted to follow up on the thing Christoph just said, which is it about formalizing the link between source languages and binary and machine languages? I think a lot of people kind of forget that there's a level of indirection here, right? Because if you're the debug format, then you're an intermediary between these. So really the job is formalizing a way to describe the many possible relationships between a source program and a binary program. And that's why we end up with a Turing powerful format, which is that it's actually the fragment of dwarf that is describing the basically locations of locals, right? So it's not so critical to the frame stuff, but if you want to allow a debugger to basically undo an optimization that a compiler has done, then for me, it's hard to see how you would get by without a language that ends up being Turing powerful. I haven't thought about that like to the max, but that's why I think that creeps in, and it's why I think it's hard to get rid of.
Mm-hmm. But it could be incredibly interesting, right, to figure out what would be a better language than DWARF to do it, right? What would be actually the state of the art today for doing something like this, describing all these different possible relationships.
Yeah, absolutely. I could, sorry, I have a thought on that, which I don't want to hijack the session, but if there's no one else talking, I can share a thought about that.
Yes, please.
Because the trend I noticed with something like, I didn't know about this gsym before, so thank you, Francesco, for bringing me up to date on that. I sense a trend in in infrastructure work that is funded by big tech players, naming no names, which is that they have use cases that they really care about, and they build something that's kind of specialized that can go really, really fast, and then reduce their bills and save them engineer time. But there's a sort of political dimension to this, which is, well, what should the format, the standard, be optimizing for? And if you look at Dwarf, it's very much like saying, we just want to support as many different things as possible. Like, we want to make it so that it can capture everything. And that is now being kind of pushed back on. It's like, no, but we can make it go faster and save 2% of our energy bill or whatever it is, if we really optimize to this case. And in some ways, I think it's an unfortunate dynamic. I think it's something that we need to notice when it's happening. There are many instances of this sort of pattern. And yeah, I just thought I'd voice that because it's kind of an interesting topic.
Mm-hmm.
Yeah, you can also use gsym to speed up just for the search, just to have efficient search of dwarf tables, because just the search in the dwarf table is rubbish.
That sounds like a clear win. Yeah, I like the sound of that.
So you can use it as an accelerator. Use all your powerful language. I mean, it is possible that the first, yeah, I mean, that definitely a use case. I mean, there are parts of DWARF that will agree are just badly designed. And also the needs are, I mean, the fact that you have basically to touch so many pages just to map one address is just not a good design.
Actually, I'm wondering, is there an issue when it comes to multi-threaded programs with all of this?
With unwinding or with?
Well, are there any like if so far we have only been looking at sequential code, right? Are there any particular issues when it comes to multi-threaded code?
Well,
dwarf tables, unwinding.
So you just what changes is where are your RSP points to, but the expressions are still correct. Your stack has been allocated somewhere. It doesn't somewhere else. It doesn't live at the top of the top of the virtual memory. It lives somewhere else. But
yeah.
Something I want to say about gsym is that if for any reason you have to do some that all the gsym files can be memory mapped by different processes in parallel. I mean, can be memory mapped by different processes, and you can have parallel symbolication. If you have lots of programs lots of stack traces to symbolicate, then you can do it in parallel, and everything works as fast as you can.
Sure, yeah, that's true.
But this is a different problem.
Yeah. Yeah, it's almost time for us.
Yep.
Any last words?
Yeah, just a question, Christoph. Did you read Julia's message on Clouder? Did we discuss it?
I did, yes.
Okay, then I guess that's the last question, at least from Clouder.
Yeah, this was on the assembly patterns, yeah. Yeah, any other last words?
Okay.
Well, then I'd say that there is a Meet the Speaker session after this, so feel free to join a coffee break room or any other Meet the Speakers room, basically.
Mm-hmm.
Yeah.
All right. Thanks a lot, everyone. Thanks a lot, Francesco, for this nice talk. Very inspiring. I also learned quite a bit. Very interesting. Fascinating.
Thank you, Christoph.
Yeah. Thanks a lot.